We are going to start this second talk. It's in charge of José Díez Albert Solé. They are going to talk about some reflections on the conditions for evidential confirmation. You have 40 minutes.
Thank you. Thanks to the organizers and to you for attending this talk. This is a joint talk with Albert, and actually the topic is really, really basic. Actually, it's his first year introductory course in philosophy of science topic, and this is how we came up with it, because we teach together an introductory course, philosophy of science, and we raise questions to the students and the exam, and there was an easy answer, which was the answer we grade. But then we start thinking that maybe there was not that easy answer. We start thinking about that, and we ended up acknowledging that we didn't have an answer for the second reading of the question. So this talk is our convoluted reflections on the difficulty of this second reading of this question. In this regard, it's an open-ended paper or presentation, so we will be very happy if you have any suggestions or comments or criticisms. The issue has to do with the conditions that must hold for some data to count as an evidence in order to confirm or disconfirm a given hypothesis. And it's of interest, of course, for theoretical scientists, but also for physicians, attorneys, detectives, or anybody interested in general in how to check an hypothesis that we cannot check directly in some other indirect manner. And of course, as you all know, this is what we teach in introductory courses. If you want to check a hypothesis that you cannot check it directly, you have to be smart and come out with some consequence of it or prediction that is able to be checked directly. And then if the prediction obtains, you are happy. If the prediction does not obtain, you are unhappy. Okay? This is more or less the intuition behind this testing hypothesis method. Here we manage two different notions of confirmation. The first one is one according to which a successful prediction confirms the predictive hypothesis, regardless the same predictions is done by other rival hypotheses. So in this sense, confirmation one is confirmation of an hypothesis independently of any other alternative hypothesis. There is another notion of confirmation, confirmation two, according to which a successful prediction confirms a hypothesis, but it does not confirm more than one rival hypothesis at the same time. So if there are many hypotheses, the successful prediction does not confirm any. Okay? We are going to focus on the second notion of confirmation, which we think is the notion of how we can call like belief grounding or belief formation, because we want to form beliefs about hypotheses that we cannot check directly through things that we can check directly. And we want to form beliefs, and in this regard, we need to compare these hypotheses with other in the context that make or make not the same prediction. So the sense relevant for forming a belief with regard to the hypothesis into play, we think is the second one. Of course, the first one has other benefits, which we can discuss later, but we are going to focus in the second notion of confirmation.
So, let me say something. Yeah. It's like a high probability notion of confirmation. So it's the sort of thing that you expect when you have the hypothesis as a conclusion of an inductive, valid inductive argument.
Yeah, this is what is going to come out now. So in order to elaborate this notion of testing with regard to the second notion of confirmation, we have the standard derivability condition, that is the hypothesis together with some auxiliaries and initial conditions with regard to the preparation of the experiment, for instance, entails a given prediction, and then with this derivability condition, we can come out with a refutation argument if the prediction does not obtain, since the derivability condition tells that if the hypothesis is true, given the auxiliaries and the preparatory conditions, then the prediction should come out. If the prediction fails, something goes wrong here. If A and IC do not go wrong, then the only option is that what is wrong is H. Okay, this is the standard notion of refutation, deductive refutation, Popper and the like. Okay. Can we do with derivability also for confirmation, not only for refutation? Well, not we cannot, as easy to show. Confirmation scenarios hold when the prediction obtains. Then, as we saw at the beginning, if the hypothesis entails the prediction holds, then we are happy about the hypothesis. But it's not possible to build an argument with the derivability condition as the only premise together with the obtention of the prediction and the auxiliaries and the initial condition. If we have an argument with derivability as a first premise, the obtention of the prediction, the not failure of auxiliaries or initial conditions, there is neither inductive nor deductive argument concluding the validity of the hypothesis. Okay? Then, as you will know, in order to have an argument for confirmation, we need another condition. Together with derivability, we need an extra condition. We call, or it's usually called, the risky condition. This condition tells that if the hypotheses were false, given the auxiliaries and the initial conditions, then very likely the prediction would not obtain. And the intuitive reading of this condition is that our hypothesis, the only thing that in that context makes us expect the obtention of the prediction. Why? Because the prediction is not very likely in itself. And in this context, we don't know, or we don't take into account any other rival hypothesis doing the same prediction. Okay? Which was basically the reason why this argument doesn't work, because the affirmation of the consequent is fallacious because we may have other antecedents implying the same consequent. So the idea is that if you grant the risky condition, you are granting both that the prediction is unlikely in itself and that there are no other rival serious hypotheses in the context taken into account doing the same prediction. Okay? And of course, with the risky condition, we can build that an inductive argument, a standard inductive argument, with the risky condition as the first premise. If the hypotheses were false with the auxiliaries and the initial conditions, then very likely the prediction would fail. But the prediction doesn't fail. If auxiliaries and IC are okay, then we are highly justified in believing in our hypothesis. This is a valid inductive argument. Then, this was the questions to other students, derivability seems to be dispensable with regard confirmation, because we don't use derivability in this argument. Okay, this was the question. There was an easy answer, which one was great, and from here on, it comes the not as easy answer that, as we say, we don't really know whether we have an answer or not. Okay, in order to be able to investigate this problem, we need first to figure out the logical form, the structure of the both conditions, derivability and risky, and then how they are related. The idea is that the answer would depend in how do we read these two conditions for hypothesis testing. Okay? If we start with derivability, with an historical example, the derivability condition, remember, is the condition we use in refutation. We have a very famous case of refutation using the derivability condition, which is the phlogiston case. Everybody here is aware of the phlogiston theory? Who is aware of the phlogiston theory? Okay, so just 2 seconds. If you look at the fireplace, besides you like it and you get warm, you or more of us, most of us are intrigued as how does the fire work, okay? And in general, how combustion works. And if you look at the fireplace, the first answer that it comes to your mind is that, well, something is going out. I mean, the combustible is in firing, it's spelling something out. Okay? Actually, this was the theory of phlogiston in the 17th and 18th century. Some people elaborated this answer. And then they say, well, combustibles, they ignite. Why? Because are made of this substance, they call phlogiston. The name is pointless. They are made out of something that ignites and goes out during combustion. Then this theory was good for many things. For instance, it explained why combustion gets extinct if you cover the combustible after firing, and many other things. For instance, the irrespirability of the air after combustion, etc. And in the 18th century, somebody, maybe Lavoisier, maybe some other guy, it doesn't matter, came out with an experiment in order to test the phlogiston theory. If phlogiston theory were true, if combustion consists in this, then if you prepare a combustible, in this case mercury, covered by a jar on a floating platform, yeah, and then you ignite with a lens the material, then after combustion, since combustion consists in expelling material, then there are less material in the platform than before. Then after combustion, the platform should refloat, go up, okay? And also the liquid around it going down, but this just with one prediction suffices. So this was the prediction made with the combustion theory. The auxiliaries, we need a lot of auxiliaries, no? We need the hydrostatic laws, we need the conservation of matter, and also the auxiliary telling that mass has, that phlogiston has a positive mass. Because when you liberate phlogiston, you refloat if you lose mass. You lose phlogiston, but from losing phlogiston to losing mass, you need to accept that phlogiston has positive mass, okay? Well, they performed the experiment, and the platform, instead of going up, it went down. So the prediction failed, since auxiliaries were considered enough guaranteed, and the performance conditions were okay, then this was a problem for phlogiston. Of course, phlogistonians, some of them tell, no, the problem is not with our theory, the problem is with the auxiliary that phlogiston has a positive mass. And they say, no, phlogiston is very weird. It has a negative mass, and it's coherent with the outcome. Okay. So this means that in this argument, in order to conclude that the hypothesis is false, you have to grant that the auxiliaries are true. And they say, no, no, here what happened is a problem with the auxiliaries, not with my hypothesis, okay? But of course, non-ad hoc people just accepted the failure of the phlogiston theory, okay? And this was a paradigmatic use of derivability condition for refuting hypotheses. So what's the logical form of the derivability condition in this argument? If we reconstruct the argument, derivability condition, the failing of the prediction, the obtaining of the auxiliaries and initial conditions, and then the deductive derivation of the falsehood of the hypothesis. If we see here, I mean, this is a modus tollens argument together with other little extra logic. This is a modus tollens argument that applies to a material conditional. Okay, modus tollens applies to material conditional. So it seems that the derivability condition here is just a material conditional. Nevertheless, is part and parcel of the hypothetic deductive method that the relation between the prediction and this antecedent is not merely material, but is one of the of logical entailment. And how does come out? Because here it seems that it would be sufficient to us to accept this sentence read as a material conditional. Why not? Well, the clue is that if we think things a little more carefully, we have these two options: the derivability condition read as a material conditional, or read as a logical entailment. And the key is to to realize that when you design a testing experiment, a testing episode, you need to guarantee the correctness, the obtention of the derivability condition before performing the experiment. Okay? You need to know whether the derivability condition obtains before doing the experiment, because after doing the experiment, if it were a material conditional, then if the prediction obtains, the material conditional would be true, but if the prediction would fail, you wouldn't know anything about the material condition, and regardless, you know already the falsity of the antecedent. Yeah.
In general, the material condition differ only because one is model dependent and the other not, or because the two conditions change. Also because legal theorists might not know.
Well, this is a logical claim.
Yeah.
This is P logically follows from that. And the material conditional is just a material conditional. It's true if the antecedent is false or the consequent is true. One is a logical claim, another is a material claim. Okay?
So, and the thing is that the natural reading of this is an entitlement, but for doing the modus tollens, you only need the weaker material thing. So we are trying to answer why actually it is an entitlement.
You need...
Because legal theories are not so into logical distinctions.
Yeah.
So for you to...
Yeah, the thing is that, well, for instance, it is true for logicians that if the moon were a square, I would be Einstein. I am Einstein. Why? Because the moon is not a square. In logic, we say that a conditional, if A then P is true, if the antecedent is false or the consequent is true. So you may have a true material conditional if the antecedent is false, whatever its relation with the consequent is. That's the tricky point about material conditionals. Material conditionals, okay? So even if the refutation argument it works as a material conditional, it's a precondition of performing the test that you should be able to guarantee the obtention of this condition before performing the experiment, and this only is given to you by the logical entailment, because you can. This is logics or mathematics. Before performing the experiments, you do the calculations. If you get the prediction, then you have the entailment. Okay? And of course, this cannot be true of the material conditional, but for the fact that the logical entailment also entails the material conditional. So the idea is that as far as you know that the material conditional is true before performing the experiment, you know that only because the material conditional follows from the logical entailment. Okay? Good.
Was that, sorry, can I interrupt?
Yeah.
Already have more about that. So I'm one of those legal theorists, but it's not very well versed in logic. But, so material then means empirical. No?
Well, everything is empirical in a sense. Material means simply that something is followed by something else. Okay. Well, not is followed. I mean, no. Material conditional means that if something obtains, then some other thing obtains. And this connection in logic is true if either both things obtain, or the first thing fails, or the second thing obtains without the first thing. So it's only false if the antecedent obtains and the consequent fails. Okay? So if the moon is a square, then I am Einstein is true. It's a crazy true, but materially speaking, it's true. Why? Because the moon is not a square. Yeah?
So maybe you can write the truth table of the material condition.
Well, the truth table, I'm not sure it's going to help. I mean, it's only false. If the simple idea is that if you claim if A then B, you tell something false if you have A and you don't have B.
In the other possible combination of truth value for A and B, the material conditional is true. So it does not require a conceptual link between the antecedent and the consequent. And that's the usual connective for implication
There is a rationale for this tricky thing, is that a biconditional is the conjunction of two conditionals. No? And a biconditional usually is true if both are true or both are false. And in order to get that, the conditional must have this truth table. Okay? But the main idea is that material conditional doesn't give you any non-contingent connection between antecedent and consequent. Everything is contingent there, okay? If it doesn't follow from a logical truth. Okay, let's go then for the risky condition, using another historical example, which is the Venus phases episode. How many of you have not ever heard about the Venus phases or the heliocentric, geocentric?
Tycho Brahe.
Okay. So maybe you know, planet in Greek means chaotic star, meaning that in the sky, along the ecliptics, this is the Earth. Then if you look at the sky, every star more or less makes the orbit continuously. But at some of them, today they show up here, tomorrow there, but then the day after tomorrow they start to going back, and they do like this along the orbit. Okay, this was errantes, crazy stars or whatever, and planets, and of course there was a tricky thing to explain this movement. The first story, the geocentric, this is the Earth, and then they say, well, the planet is moving around a point that moves around the Earth. And then if you combine this movement from Earth, you see this. Okay? Then from later on in 15th century, Copernicus, as you know, he defended that the sun was at rest at the beginning, the Earth was here, and then the planet was around the Earth. And with this construction, from the Earth, you have the same appearances. Okay? So we have these two rival systems, astronomic systems. And it's interesting that these are the two systems. It's interesting that for fitting the particular retrogradations of Venus, the center of the deferent of Venus should be aligned with the sun. Okay, the center of the deferent of Venus is aligned with the sun. Otherwise, you don't get these appearances. This means that in the geocentric case, which is this one, this is the Earth. Then we have the Sun, the Venus, when Venus is closer to the Sun or closer to Earth. And as you see in this drawing, in both cases, Venus is almost black seen from Earth. That is, Venus doesn't show phases, strong changes. Okay, but in the heliocentric system, with the Sun in the middle, Venus around the Sun, and Earth around the Sun, when they are in opposition, you have almost full Venus, and when you are... What I did?
Random slides.
How many?
Some randomizing.
And in the heliocentric case, when they are aligned, on one side from Earth you see almost full Venus, and on the other side you see almost black Venus, empty Venus. Okay, so in the heliocentric case you must see strong phases, a strong change in Venus appearances around Venus orbit. Okay, this was the different predictions from both theories, and then, as some of you know, this is what happened. Venus has strong phases, enough strong phases. Of course, this was taken, for one thing, as a refutation of Ptolemy, of geocentrism, okay, because the prediction failed, and then a confirmation, because it is square with Copernicus' prediction, okay? But this observation would not have seemed as strongly in favor of Copernicus to Tycho Brahe. Tycho Brahe, who was a guy who some decades before had a third system with the Earth in the middle, the Sun turning around the Earth, and the planets around the Sun. this system is equivalent with regard this phenomenon. So if you see phases from the Copernican system, you see phases from the Tycho-Brahe system. So Tycho-Brahe system also...
To Copernicus. It has the same prediction.
Yeah. It's what is called technically the empirical equivalent modulo this kind of phenomenon. Okay? So this means that both Tycho and Copernicus, they made the same prediction. Then the question naturally arises. How can we take this prediction, which is made both by Copernicus and by Tycho Brahe, not only a refutation of Ptolemy, who predicted it wrongly, but also a confirmation of only one of them, of Copernicus and not of Tycho Brahe? Well, there is only one answer. Because in 1610, when this prediction was observed, Galileo took it as a definite confirmation of the geocentric system, simply because Brahe's system was not taken into account in that context as a rival hypothesis. Had it taken into account, we would have had two different hypotheses with the same prediction, both playing the game in the same context, and we would have not been able to choose between them, okay, to adjudicate between them. What's going on here? The risky condition. The risky condition, recall, it tells something like the following. The prediction itself is not likely in itself, so it's not that you can expect in itself phases on their own, but also the prediction is not known in a given context to be predicted by other acceptable rival hypotheses. And then we informally write the conjunction of these two ideas by this. If the hypotheses were false, then very likely, this is the only way we try to coin this pragmatic conjunction, the prediction would not obtain. Okay? Given the context, these two things happen, so we would not. The only reason in that context to expect that the prediction obtains is given our hypothesis. This is what the risky condition tells. And then the thing is, what's the logical form of this condition? Well, this condition is more or less pointed out by other authors, Carnap, Popper, Gire, Mayo, and some others. Yet they don't enter into the issue of what's the logical form of this condition, trying to make the not presence of rival hypothesis explicit. And then we are going to check different possibilities for the logical form of this condition. This is the informal writing, and then the first option is to check whether the risky condition is a material implication. From now on, we are going to get rid of auxiliaries and initial conditions, just for the sake of simplification, and nothing hinges on that. Okay, so the first possibility is to take it as a material conditional with the falsehood of the hypothesis in the antecedent and a probabilistic consequent. If the hypothesis is false, then materially, very likely the prediction does not obtain. Okay? This condition as derivability must be known before performing the test, and this material conditional can be known before performing the test. Sorry. Why? Because we can know whether something is very likely or not, independently of whether it obtains or not. Okay? Suppose that the likelihood of P is affordable before even noticing whether P is true or false. Okay? So in this regard, the material conditional satisfies the constraint of being knowable before performing the test. So maybe this is the correct reading of the reasoner's condition. Is it? Well, let's see with another example. Take this argument. If Fresnel law were false, Fresnel law has to do how light moves or whatever, okay? Then very likely no new star would appear in some moment of time in some region of the sky. For instance, we regard the appearance of the Halley comet in certain moment in the history of astronomy. Then the star appears in that place at that time, thereby Fresnel law is correct. This seems to have the same form as the standard confirmatory arguments that we have seen with the phases, with the Venus case, okay? If my hypotheses were false, then very likely these things would not happen. This thing happened, then confirmationally my hypothesis is correct. But intuitively there is something wrong here, no? How on earth can I confirm Fresnel hypothesis just checking whether a new comet, no? There is something wrong here. What is wrong? Well, we assume that the appearance of a new star in that conditions is very unlikely, so the first premise is true. We assume that Halley appeared, the comet Halley appeared in that circumstances. The second premise is true, but we wouldn't say that this makes probable that Fresnel law is true. Okay. Okay. So, since if premise 1 were a correct expression of the risky condition read materially, this argument would be a bona fide confirmatory argument. But intuitively, this argument is not a bona fide confirmatory argument. Thereby, the first premise cannot be read materially. Okay? We can show this more easily here. In general, this is the first premise. If not H, then materially, very likely not P. P, thereby very highly probable H. This is an invalid argument. Why? The first premise, not H, then very likely not P. In logic, we say that alpha, then beta is equivalent to not alpha or beta, as we say, because it is true if the antecedent is false or the consequent is true. So the first premise is equivalent to what? My hypothesis is true, or very likely the prediction is false. Yeah? And as you can see, both premises may be true, just because P is very likely not to obtain, but nevertheless obtaining. This is perfectly compatible. And we cannot tell that H is going to be very likely then, because there is no connection at all between H and the likelihood of P. The thing is that material connection between H and the non-obtaintion of P in the risky condition does not give you the necessary connection in order to the confirmation getting a consequence about H from information about P. You need a non-material, non-merely contingent relation between H and P in the risky condition. This is the intuition. This is why we don't accept the Fresnel argument as a confirmation argument for Fresnel. Okay? So, is there a way of improving this argument in order to get H as a correct inductive conclusion, maintaining the material reading of the first premise? Well, since the problem was that the first premise materially read does not give you any not merely accidental connection between H and P, one can say, well, maybe if we add derivability to these premises, derivability ties hypothesis and prediction, not materially. It ties them necessarily. Maybe we add derivability as an additional premise, we get a correct inductive argument. And we have this. The material reading of riskiness, then the derivability condition, then the obtention of the prediction, and then as a candidate for an inductive valid conclusion, the truth of our hypothesis. Is this argument inductively good, well situated, cogent? Unfortunately not. Why? Precisely because of the possibility of rival hypotheses also entailing the prediction and also materially connected with the unlikelihood of the prediction. So the problem of the alternative rival hypothesis just reappears. And we are not going to fix it with this reading. It seems then that there is no way of excluding the alternative hypothesis option with a material reading of the risky condition. We have to try another logical analysis of the risky condition. Which other options we have? For instance, we can try with conditional probabilities instead of material conditionals. Let's try the conditional probabilities reading using this other example. If the mayor does not, I guess that most of you know the relation between syphilis and paresia. Paresia is an illness that develops if you have had untreated syphilis, but only 25% of the cases. Okay? So there is a connection, but very statistically not that high, but you cannot have paresia without having syphilis, bad by mutation or accident or whatever, but in general, 25% of untreated syphilis give rise to paresia. So consider this argument. If the mayor does not have syphilis, then very likely he does not have paresia. The mayor has paresia, then very likely the mayor has syphilis. This argument intuitively is cogent. Intuitively, you can be confident that the mayor has syphilis, given that the mayor had paresia. Okay? Then let's try to read the first premise in terms of conditional probability. Forget now then about material conditionals, and let's try conditional probabilities. What's the way of reading this? The essential point is that in this case, contrary to the Fresnel case, there is a non-contingent connection between the hypothesis, syphilis, and the evidence, paresia. And it seems that this is the tricky thing, that we have to be, that we must be able to, in our formalization, in our scrutiny of the logical form, to come out with this non-contingent connection between the hypothesis and the prediction. And then, what's the option we may have? Well, remember that the probability here of having paresia given untreated syphilis is 1/4. In any case, the probability of having paresia without having had syphilis before is almost null. Okay? So the untreated syphilis increases a lot the probability of paresia, although only up to 25%, but from almost 0 to 25%, which is a considerable increasement. So maybe this is the condition we are looking for, just that syphilis increases a lot the chances for paresia. So maybe this is what we are looking for. The probability of the prediction given the hypothesis is much higher than the probability of the prediction not given the hypothesis, okay, even if, as in this case, the phenomenon, the prediction, is not entailed by the hypothesis, but only make it probable. For those who probably are aware that this is the standard first trial probabilistic reading of causal connections, with all the problems with common cause and all that, it doesn't matter to us, because even if in the barometer case we have a common cause and we cannot extract conclusions about the causal efficacy of the barometer, we still can have conclusions about the confirmatory role of the barometer. So this is not a problem for confirmation. It's a problem for causal claims, but not for confirmatory claims. So we can try to do with this condition. Nevertheless, at best, what this captures is the non-contingent relation between the hypothesis and the prediction. But it does not exclude the presence in the context of rival alternative hypotheses also doing the same prediction. So maybe we can preserve this as a formal version of the non-contingent connection between the hypothesis and the prediction that we saw contrasting the Fresnel cases and the syphilis cases is necessary for confirmation, because without this non-contingent relation, then the argument is logically invalid, intuitively. So this could be a way of formalizing this non-contingent relation. But since it does not exclude the alternative hypothesis option, maybe the correct formulation is this one plus something else. And what else can this be? Well, one option is this, is that the probability of the prediction given the failure of the hypothesis is low. What's the intuition? We want to exclude other hypotheses that make the same prediction. This means that thinking of our hypothesis being false, then the probability of the prediction is very low. Intuitively, this seems to mean what? That there are no other predictions doing the same, other hypotheses doing the same prediction. This is the intuition we are pushing after, okay? This is more or less the representation of that. But unfortunately, as this representation shows, it doesn't work, and this example shows you. Where is the example?
No, el anterior.
No, what example? Okay. Well, this diagram shows you that this extra condition, okay, does not guarantee the absence of rival hypotheses doing the same prediction. So what about this other option? The probability of not H given the prediction is low. What's the idea? This is the prediction in the logical space. The idea is that the bigger H, the bigger our main hypothesis, the fewer the space for other rival hypotheses. Okay? So the idea is that if the probability of not H given P is low, because H fulfills a lot of the P space. So there is little space for rival hypotheses. Okay? This would be intuitively the rationale for this alternative completion of the main hypothesis, of the main reconstruction. Well, unfortunately, there is a problem, is that if this condition is fulfilled by H, is also fulfilled by H, and it's disjunction with any other hypothesis here. And usually we don't want to confirming disjunctive hypotheses. No? Scientists, lawyers, detectives, they are not interested in confirming. And according to this, it would better confirm a disjunction than the original hypothesis. Okay? So it seems that, pragmatically speaking, this is not what is going on in scientific or detectivist reasoning or whatever. There is another problem, but we can discuss it later. So it seems that neither a material conditional with a probabilistic consequence nor a conditional probability seem adequate to capture risk. We have not been actually able to come up with different satisfactory formal analysis of riskiness, and given the highly contextual pragmatic nature of this condition, we are pessimistic that this can be done. Of course, we could define probability star notion, meaning the probability star of P is high when P is unlikely in itself, and there is no known acceptable hypothesis in the context predicting P. We can coin this notion of probability, but we wouldn't explicate anything. Okay? This would not have any explicatory insight at all. So we believe that this extremely pragmatic, context-dependent notion of risk in the confirmation scenarios are really evasive to be formalized. And this is extremely important, because notice that the inductive argument the inductive force on the inductive argument depends on the quantity of the probability measure of the first premise. The higher the probability in the inductive premise, the higher the inductive support. But if the probability in the inductive premise is this kind of pragmatic contextual probability unable to be captured in any standard manner, then the inductive support that comes out to this probability inherits the same tricky nature. So confirmation has, the inductive support of confirmation has this tricky nature. And if we are right, if you have a better option to analyze it, then we are happy to withdraw, but as far as we can tell, we are skeptic that this can be done. So just 5 minutes, have 5 minutes to conclude. Then what about the relation? Remember that all this was to answer the easy question we put to our students, whether derivability was dispensable for confirmation or not. And well, we have seen that in order to do that, we should be clear about the logical form of two conditions. Derivability was clear. Riskiness, actually, we are right, it doesn't have a, strictly speaking, a non-logical form, but has this pragmatic, unanalyzable character. And then what happens with the relation between them? Remember that derivability just tells you that there must be a positive relation between the hypothesis and the prediction. And riskiness tells you that there must be a negative connection. What happens with the prediction if the hypothesis doesn't obtain? Okay? These two things seem to be in place, necessary, but as the paresis argument shows, the positive connection between the hypothesis and the prediction need not be, for confirmation, one of entailment. Because the non-contingent relation between syphilis and paresia is not one of logical entailment. It's not contingent, but it's not one of logical entailment. In fact, it's statistically very low, it's 25%. But the important thing is that it's not contingent. There is a 25% non-contingent relation between these two phenomena. So then, is, in fact, derivability dispensable? Well, derivability is not dispensable for testing hypotheses in general. Why? Because before we perform the test, we don't know whether the outcome is going to be positive or negative, and we want, if it is negative, to be able to construct a refutation argument. And for a refutation argument, you need derivability. You need an entailment connection between the hypothesis and the prediction. Okay? So if your testing is going to be designed in need of applying refutation, then derivability is necessary. What about confirmation? Well, as just said, with regard confirmation, derivability seems dispensable. What it doesn't seem dispensable is the assumption that there is a maybe not logical, but for sure non-contingent connection between the hypothesis and the prediction. Because the inductive argument only looks cogent if the relation between the hypothesis and the prediction is non-material, is non-contingent. So if the confirmation argument has as its only substantive premise, together with the prediction, the risky condition, then this idea of a non-contingent relation between the hypothesis and the prediction must be plugged in the risky condition. Because the risky condition read without this doesn't give you an intuitively valid confirmational argument. This means that maybe the intuitive reading of the risky condition includes as a pre-assumption that there is a non-contingent positive correlation between the hypothesis and the prediction, which is, as far as I know, something that nobody has done before. I mean, it's just something that probably is assumed, but it has not been explicit before. And then, together with this pre-assumption...
Sorry, but here the emphasis is not only on the non-contingency, but on the positive.
And the positive correlation. Okay? maybe not of deduction, but so the idea is that in order to confirm, we have to grant these three things. In order to refute, we have to add that this non-contingent positive correlation is one of logical entailment. Okay? But this is only if you want to apply refutation given the failing of the prediction. So it would be like for performing a test, these three things would be always necessary, and if you want to extract a refutational conclusion, the first condition would be, should be one of logical entailment. But for confirmation, this would not be the case. This would need not be the case. Okay? So, well, this is something that we tried to formalize before with conditional probabilities, but it doesn't work. The idea is that this didn't exclude the problem alternative hypothesis, but it is still may be open whether these two conditions, though not sufficient, may be necessary. And then the question is there any other probabilistic condition that added to these two give you necessary and altogether sufficient conditions for capturing this risky idea that we thought is the essence of the testing process? If there is, good news. Otherwise, there is no way of formally analyzing to the full the confirmational process of testing hypothesis. That's it.